Hey everyone, my name is Derek Lemon. I work with Cisco Systems. I was one of the original engineers to implement and kind of POC Kops on Openstack. Just as a kind of query, how many of you use Kubernetes today? Okay, that's good. How many of you are familiar with Kops on AWS or Google? Anybody? Okay, that's great too. So as an agenda today, I'll give you a little bit of an introduction about myself, a little bit on Kops since it looks like a couple of people aren't familiar with Kops. Some motivators of why we chose to kind of POC moving to Kops versus some of the existing tools that we were using, and then several demos of Kops running against OpenStack, and then hopefully some time for some questions. So as an introduction to me, that's my GitHub handle. If anybody wants to look me up on GitHub, see any of the projects that I've been working on. I started as a C++ engineer, kind of transitioned into Java, Go, Python, several languages, maybe about 8 total. And I also have experience running every single cloud. Well, every one of the large clouds. There's obviously some clouds that I'm not familiar with, like Alibaba and some of the smaller ones, DigitalOcean. So a little bit about Kops. Kops is one of the more popularized tools to provision a cluster, specifically on AWS. But it's gotten a lot of traction in Google, and now we're using it internally to deploy clusters in OpenStack as well. It runs a little differently than some of the other tools. I think one of the first tools that I used was Heat to deploy a Kubernetes cluster. And that's very imperative. It takes quite a while to get something up and running. This tool is a little different. It follows the Kubernetes design philosophy of you declare a state, and then you have a controller which is responsible for reading that state and making the desired state of the world the actual state of the world. So we will go through some of that in the demos. Also, Kops now supports most cloud providers. A lot of those cloud providers are alpha, so it does have AWS support, Google support, and a lot of feature-gated support. So it does have Alibaba, DigitalOcean, and now OpenStack. And then it's intended to be production grade. So we're not going to allow you to do just some of the things that you might want to do, like deploy a Kubernetes cluster without, say, load balancers on it. We'll block you from upstreaming some of those changes. So a couple of the motivators for me, specifically, I really wanted instance groups on my Kubernetes clusters. A lot of you are maybe familiar with instance groups if you have GPU workflows. I wanted instance groups for maybe multiple node flavors because you might, say, have a group within your company that wants to deploy a 128 gigabyte memory database. You don't want all of your cluster to be 128 gig nodes, so that would give you that capability. It also allows you to deploy multiple node images. This was beneficial at the time. We were experiencing some trouble with CentOS, and we decided to try out some Ubuntu nodes. So to test those side by side was beneficial for us. Also to kind of deploy and replace nodes that were different distributions was beneficial. It also allows you to declare node taints and labels. Node taints being specifically good at denying scheduling to a certain set of nodes, isolating those nodes, and being able to add tolerations to a certain set of pods which are intended to run on those nodes and not experience a whole bunch of noisy neighbor issues. And labels being specifically designed to schedule to particular nodes, which would allow you to use an instance group label, for example, to schedule to those nodes. etcd is designed a little bit differently than what we were using. etcd is backed by disks. In this case, we were using a tool which had been writing etcd data directly to the OS file system. It increased performance, but it was hard to snapshot, hard to migrate. And now we have disks with the etcd spec on the disk label, which allows us to move etcd, and it will still know what member of the etcd cluster it is. The time to provision is way down as well. For example, some of our overseas employees deploying to an Openstack instance in the States, they would take somewhere on the order of hours. Now it's down to under 10 minutes. So the first thing I want to demo, and these demos aren't live mostly because of trust issues, but I will define objects, and I will show you those objects in code, kind of to give you a feel for what I'm defining. It's not very granular. It's a very high-level description of what a cluster and an instance group are. And then I will push those objects into object storage, and then I will execute my control loop. So first, let me show you the object which I will deploy, which is a cluster object. There's several objects in here. Most of this will look familiar to you if you've used Kops on any other cloud. For example, AWS looks very familiar. There are a couple of differences. OpenStack requires a lot more variables on how your OpenStack deploys or is deployed. There's a variety of OpenStack instances out there that we're trying to support. For example, I don't particularly have Octavia support, but that is something that we've already merged in. You do have to specify your external network for your router, for example. And then most of this is the same as AWS. At the bottom of this file, we've defined 3 instance groups. 4 instance groups, 3 for the masters, and then 1 node instance group. It should be very similar to standard deployments. So I'll go ahead and run this demo. Let me know if this text is too small. I can maybe make it larger as well. So this will play right through, potentially faster than desirable, but the steps here, there should be essentially 3. You source your OpenStack credentials so you can communicate with the API, and that's an example of us. We're authenticated. And just to demonstrate that there are no servers, there are no containers, and my container will be considered my state store. I will export a state store for Kops, which is similar to AWS. However, this time we're going to use Swift instead of something like S3. And then I will create that file that we just showed that had the cluster and the 4 instance groups. Sorry, 5 instance groups. I skipped over Bastion. And now you can see we do have a container, OIS, and if we describe the objects in there, that is exactly what was output above, being the cluster and all of the instance groups. We also need to create a key to be able to SSH into the Bastion. And then we need to push that key into the state store. So after we push that key to the state store, we'll be capable of listening in the state store once more, except this time we'll have an additional element under PKI. And now what we can do is we can actually run our control loop. I'll first show that there's no servers, and then I'll execute my control loop surrounded by date timestamps. This ran on Friday. This should be fairly accurate to how long it actually takes to execute a control loop. This was one of the motivators for using Kops, was how quick it was to provision a cluster. Obviously, a lot of our development is around this tool, and we want to be able to execute our tests rather quickly. So that started at 8:03, just for reference. And some of these happen quickly, and there are issues. For example, there's this reported issue that goes into an error backoff that eventually resolves. We should get another one. So that is an error saying that you can't add a master to a pool because its network isn't provisioned. And now I can execute OpenStack server list to indeed show that there are the appropriate nodes of a Kubernetes cluster provisioned. And we can look at some OpenStack objects to just kind of give an example of what this looks like. One thing that maybe went too quickly by was the end timestamp, which was 8:06. So within 3 minutes, we've provisioned everything we need to in Openstack, and specifically Cisco's Openstack. Every Openstack will take a different amount of time to provision nodes. And at the end of that output, it had stated that your cluster will be ready in a couple minutes. And the way that this is different is we declare what we want on our nodes. So when the node starts up, it's got a specific amount of user data to provision itself. And then it also pulls down a service which does all of the wiring. So mounting etcd to the appropriate nodes and being able to connect all nodes to the API server's address. So that is kind of what the control loop looks like. The next thing that I'll demo is kind of a validation. And we've kind of already done validation ourselves. What validation is looking for is that your checked-in state to your object store or your state store is the actual state of what's deployed. This can be ran manually after you deploy a cluster, or it can be ran in CI/CD. So again, we reference the cluster name. We tell it where our desired state is, and then we execute validate cluster. And validate cluster reports the following back, essentially that you have all of the instance scripts you want, and some of the nodes that you've deployed are ready. Now this one was a little bit different than the provisioning. I've recorded these demos against different clusters that we have deployed with Kops. For example, I already have an instance group created on this one. So let me demo updating, and just to go over what we're going to do in the update demo, since it's recorded, we're going to add an instance group to an existing cluster, one that was as bare as the first cluster I created, and then we're going to run our control loop to make sure that that state actually gets deployed, and then we'll probably run a set of pods which schedule to that instance group specifically, and then delete the instance group. So this will go by quick. This is essentially one of the pods that we're going to try to deploy. It's got a scheduling constraint and a toleration for an instance group which is tainted. That is the object that we're going to be creating in Kops, which is an instance group object with that taint, and also a node label which we can use to schedule. So we'll first push the objects to object storage. And then we will run our control loop. So this should look from a tool very similar to kubectl, if a lot of people use kubectl or kubecontrol or wherever that debate has led us to. And then immediately after this control loop runs, since it will take a while for these instance groups to provision themselves, you should still be able to see them in Openstack. So we will list the servers. We have an instance group with 2 nodes that's called load test. And we indeed have 2 servers in Openstack called load test. You can see also from the output there that those nodes are of a different machine type. And then we will again try to deploy or create this deployment in Kubernetes, which has a match expression for scheduling on that instance group and also a toleration for that instance group's taint. We've created that deployment. We can list the pods. And indeed, we see that that one is on that instance group. We can scale the pods to prove that that just wasn't luck. This, again, is very separate from Kops. You can do this almost on any cluster. The added benefit you're getting with Kops is being able to do it in a declarative way. So again, we've scaled to 20. We have 20 of those pods running on those isolated nodes, and we can scale to 50, and it still holds true. So the next thing I want to do is destroy this instance group. Actually, yeah, here I'm actually going to scale the instance group. I wanted to prove that instance group scaling works. So if you did have a cluster of a specified size and you wanted to grow it, this works on both the node instance group or this custom instance group that I made. And this might not display that great, but basically what I'm doing is editing the max size of the instance group object which I created previously to 4. And then that will automatically update the state store, which in this case is Swift, and then I will run my control loop. There's actually multiple ways of using the create command for this cluster. I've chosen to show a declaration of a cluster because that fits better in kind of a GitOps workflow. All my tasks are done. A lot of these tasks, though it shows 136, skip. They essentially are no ops, except for the instance tasks and the port tasks associated to those instances. You can see now that we have 4 load test servers. So again, it's scaled. It's scaled rather quickly. It takes way less than provisioning the whole cluster. It's on the order of maybe 2 or 3 minutes for myself. And again, those slowly come up because they're responsible for their own provisioning. And now we will delete the instance group. And this one will actually both update this state and then run the control loop. So again, we can list the servers, and we can see that those are gone. And then we can query the API server to make sure that the nodes are actually gone as well. And those, I believe, should remove themselves after a certain amount of delay. So that's instance groups. I want to go over cluster deletion. There was a couple of nice to haves here for cluster deletion. This declares every resource that's created in Kubernetes and every association between resources in Kubernetes as objects that are executed as tasks. And when you delete those objects, you essentially are deleting every single one at a time. We've had problems before where we would try to delete a load balancer, and then it tells you, oh, delete my listeners, and then, oh, delete my pools, and oh, delete my health checks. And it was very painstaking. But I will demonstrate what cluster delete looks like. So again, this should be very similar to deleting an instance group, except we're going to delete the file, which declares all of our objects. Or we can delete the cluster by name. So again, it's attempting to delete all objects, and then it will run an error on some, and then some will go into an error backoff, where it'll progressively wait longer and longer to delete those objects. So here we have an error with routers having ports associated to them. And eventually those resolve. And then it will say both that the cluster is deleted and then the objects in that container will be missing from Swift, and it will update your Kubernetes config file to remove that context from the config, defaulting to localhost. So there are a couple of challenges. This is kind of relatively new. I think I got this merged in January, late January. There's a diversity of OpenStack deployments. Some have came trying to deploy Kops against their Openstack with little success because of different configurations. We do have a couple of individuals in various companies using this at this moment with success. This is marked as alpha, as I'll point out. So we have a limited amount of developers, and this is still a growing effort and relatively new. There's not yet support for designate. These are kind of planned future additions. Once I get support to designate, that'll probably be one of the first tasks I work on. And also no parent controller for rolling updates. So as this was created for AWS or with AWS in mind, even Google has a similar concept of auto-scaling groups. AWS creates their instances by defining auto-scaling groups, and we had chosen not to use Heat. So Kops creates those instances directly. And when you run a rolling update on a cluster after you've made some kind of state change, what Kops will do is go and delete your instances. In the case of Openstack, it will delete one instance and expect you to restore it with running the control loop again. I would like this to change. Currently, it doesn't harm anything other than being extremely annoying to use. And that's about it for demos. I'll take any questions if anyone has questions. Yes?
What are the differences between this and OpenStack Magnum?
Magnum, I haven't used. I remember that came out in like 2016. I even heard about that. But basically, one of the motivators that I probably didn't describe is we were already using Kops for AWS, and we were using some other tool, and it could be any other tool. We were using Kubespray. And we wanted to kind of consolidate our tool set, so we just added the work into Kops. It was already really close. There's been a lot of individuals who have contributed to the effort, and now we have kind of the same tool set that we use for AWS and OpenStack. So, but I'm not very sure on how Magnum works. So, any other questions? Yes. I think what tool are you on right now? I might be familiar. Is it Magnum or Heat? Well, I guess it would depend on how Heat works. So if you're using Heat to provision the nodes and then using Ansible to install Kubernetes after that, there's no step where you're creating kind of a client-to-server command of, hey, go create a cert, and hey, set up the etcd server, and hey, do this. We're telling the nodes individually, this is what you need to install on yourself, and then we run a service on those nodes, currently called ProtoCube, which will say, hey, OpenStack, tell me who has a disk mounted to that server with my etcd label. So it does the discovery on every single node at the same time, and then all of the installation of everything simultaneously as well. I think that's probably a large reason why it's faster. But again, I've never had that much of a fast experience with Ansible, so I don't know what's going on under the covers there that might slow things down. So yeah, if that answers your question. Any other questions? I want to skip ahead. Okay, thank you, everyone.